ecce agnostai qui tollit peccatum mundi. Behold the Lamb of God, which taketh away the sin of the world. Jesus Christ, the Lamb of God, changed the world forever. The effects of this can be seen even in science, technology, history, art, and culture. In this podcast, we explore these effects and learn what it means for us today to follow the Lamb. I'm Joshua Göcking, and you're listening to the Follow the Lamb podcast. Episode 12. Symmetries as an evidence of creation. So in this podcast episode, I will talk about an article that I was allowed to write for the journal Studium Integrale. It's the volume 32, issue 2, and this is published by the study group Wort und Wissen, in which I'm engaged, for which I also wrote some articles already. And without further ado, I want to dive into this article, and I hope you can really understand what I'm talking about there. It's about symmetries and whether they can be an evidence for creation or for a creator. So, we encounter symmetries in many places in nature. The wings of butterflies, ice crystals, and even the human face can be considered approximately to be symmetrical. Human perception usually perceives symmetries as something beautiful, and they are of great importance in art and architecture. In physics, the concept of symmetry can be further generalized and an interesting connection can be made. For example, the laws of physics are symmetrical with respect to time shifts. So when we talk about symmetry, we usually are referring to mirror symmetries. However, there are other types of symmetry. For example, an object can also be symmetrical with respect to a rotation by a certain angle. In many cases, these symmetries serve a specific purpose. For example, double-headed snakes look the same from the front as they do from the back and are therefore rotationally symmetric under rotations of 180 degrees. When attacked, they raise their tails to deceive the attacker about the actual position of their heads. So what exactly is a symmetry? In the case of mirror symmetries around a specific axis, symmetry means the following. If everything on one side of the axis is transferred to the other side, it looks exactly the same as the original. A rotational symmetric body still looks the same as before, even after being rotated by a certain angle. This is the case with many flowers. In general, symmetry can be defined as follows, according to physicist Hermann Weyl. Something is considered symmetrical if you can do something to it so that after this action it looks exactly the same as before. This definition can be used to find symmetries beyond geometry. For example, symmetries can be found in mathematical equations. Such symmetries can be discovered particularly in the mathematical description of physical laws. The equations of motion in physics are invariant, that is, they do not change with respect to the transformation of certain variables. For example, the equations of motion do not change when the time is transformed, that is, regardless of when a throw is made, the trajectory does not change. The laws of physics are thus invariant or symmetric with respect to time translations or time shifts. The transformation with respect to which the mathematical equations are invariant can be derived analytically. This involves using the principle of least action, which states that a system always strives to minimize the energy required for the process. This can be illustrated by the paths of light. Light travels at different speeds in different media depending on how strongly it is refracted. If light has to pass through several media on a route between 2 points, for example through water and through air, the path is not the shortest route, but the path where the sum of the shortest times is required for the passage. This is then the path in which the light reaches the destination the fastest. This situation can be compared to a lifeguard who, in order to rescue a drowning person in a lake as quickly as possible, takes a longer route along the shore because he can move faster on land. If we calculate the paths of light and minimize the time required, we obtain Snell's law of refraction. This principle of the shortest times of the paths of light, or more generally, the minimization of energy required, can be formulated mathematically. The effect is calculated, or the action is calculated, which has then to be varied to determine the minimum. The results are the so-called Euler-Lagrange equations. From these we obtain the Lagrange function, which is of great importance in physics. It allows us to clearly determine whether the symmetry under the transformation of a certain whether there is a symmetry under the transformation of a certain variable. If the transformation of the variable changes the Lagrange function only by a time derivative, it will have no influence on the equations of motion and thus behave symmetrically. The importance of symmetries in physics becomes clear when they are linked to conserved quantities. Conserved quantities do not change and are at most converted into different forms of transfer to other bodies. An example of this is energy conservation. In a swinging pendulum, the energy is conserved throughout the entire swing and merely oscillates between kinetic and potential energy. Kinetic energy is the energy contained in the motion of the body. Potential energy is the position energy, that is, the energy that can be converted into kinetic energy due to the deflected position of the pendulum by the force of gravity. Noether's theorem establishes an interesting connection between symmetries and conservation laws. So, Emmy Noether was a mathematician who also contributed to theoretical physics. Her greatest achievement in the field of theoretical physics is Noether's theorem, named after her. It states that every symmetry results in a conserved quantity. Symmetry here refers to symmetry in the sense that I previously derived in physics. If such symmetries can be found in the physical system under investigation, it follows that there is a quantity that is conserved in the system. According to the theorem, the following conservation quantities underlay the common symmetries. Energy conservation follows from the homogeneity of time, that is, the fact that as described above, the outcome of a physical process does not depend on the time at which it is performed. From the homogeneity of space, that is, the fact that the outcome of a physical process does not depend on where in space it takes place, follows the conservation of momentum. From the isotropy of space, that is, the fact that the outcome of a physical process does not depend on the orientation of the system in space, follows the conservation of angular momentum. The symmetries shown here relate to space and time. Symmetries that indicate physical conservation quantities can also be purely mathematical symmetries that do not specifically relate to space and time. And we want to look at one of those, and this is our phase transitions in quantum mechanics. So in quantum mechanics, we can do such phase transition. And what this is so quantum mechanics is described by wave function. You can get this wave function using the Schrödinger equations, and these wave functions usually contain complex numbers. So complex numbers are an extension of the real numbers, and the real numbers are the numbers that you know from the number line. This is the set of all integers, so 1, 2, 3, 4, 5 and minus 1, 2, 3, 4, 5 and so on. Then numbers contained by fractions of those integers, and then also transcendental numbers like for example the number pi. The extension to complex numbers is achieved then by assigning a solution to the formula x squared plus 1 equals 0. Because if I calculate that, I put the 1 on the other side and I have x squared is equal to minus 1. I take the square root, and if I only stick to the real numbers, I don't know what to do now, because there's no solution in the real numbers for the square root of a negative number, and therefore I decide to just define it as a new number, and this number I call I for the imaginary unit, and this number I is now basically what happens when I take the square root of -1. Or in another way defined, if I square I get -1 as a number. And if I now have this new number, I can build a complex number which is consists of a real part, so a number in the real numbers, and also an imaginary part that consists of a number that consists also of a real number, but is where this imaginary unit is added. So then this complex number would be something like, complex number Z is something like A, some real number, plus bi, where b is also some real number and I is the imaginary unit. If we consider the real part and the imaginary part as coordinates, so we have now this complex number and we consider the real part and the imaginary part, we split them up and consider them to be coordinates, then the complex number can be viewed as a point in a two-dimensional plane. So if you just imagine a two-dimensional plane where you have an x-axis and a y-axis, and then on the x-axis you say you have the real part of the complex number, and on the y-axis you have the imaginary part of the complex number. And so you can basically describe such a number as a point in there. So if you have, for example, the complex number 2 plus 3i, then you have to go in the coordinate system to go 2 to the right on the x-axis and 3 up on the y-axis, and this point then would be a representation of this complex number. And you can, of course, if you now look at this closer, you can see you can draw a line from 0, 0 into this point, and then you will also have another way to show this number, and this is by this line, the length of this line, which we for now call the radius, and then also the angle that is between the x-axis and this line, which we will call the phase. So, and this radius is called a radius because what it is basically a radius. It's a distance, and you can compute it following the theorem of Pythagoras. There you can see that if you take the x-axis and the y-axis, and you see then they enclose a rectangular triangle with this point, and then you can use the square sum of those and take the square root to get the length of this radius. So this is the one quantity, and then you have also this phase between this point in the complex plane and the x-axis. So what's now important is that what for physics is important, so does this all mean physically? So we saw these complex numbers are in the wave functions and they are used there, and what does this wave function physically mean? So if I take the square, so this radius basically, and if I take this, then this gives me a probability in quantum mechanics. This gives me a probability of something, that something will occur. But then you can realize, okay, if it's only about this radius, I can basically turn this point of my complex number, and as long as I keep the radius constant, I will have the same result. I will, if I only take this radius with me and leave the phase B, then I can get the same result no matter where I will be on the circle with this radius. So I can, in the plane, I can then basically draw a circle with this radius, and every point on this circle will have the same radius, the same length, the same length, and therefore the same will have the same quantity as the one complex number I mentioned before. It will have a different phase, but since this phase does not matter, I can forget about it. And this means that the physics, quantum physics, is symmetric under these phase transitions. So if I make a phase transformation in this plane, then this does not affect quantum mechanics, and this symmetry has also a conserved quantity, a really basically physically conserved quantity, and what's conserved here is the probability. So I said that these these wave functions describe probabilities, and of course you can only have a probability of at most one of something happening. That a probability of 1 that something will happen, or 100% that something will happen, mean it will happen to 100%. It will happen. So it can, and you cannot have more than that. You cannot have it will happen more certain than absolutely certain, right? So therefore the probabilities that we deal with in quantum mechanics need to be conserved. It cannot be that there are basically probabilities that are higher than 100%, and this is taken care of by this symmetry. This symmetry leads to a conserved probability. If we now go further into quantum field theory, then it gets really interesting, because there we will also have these complex phases, or these phases in a complex plane that are where the physical equations are invariant under it. However, they are in this case now, in general, they can be more dimensional, and they can also have be not local anymore, but be depend on where in space you are. You can have a different phase, and this leads to interesting terms coming up, interactions terms we call them, because they lead to interactions of for example, the electromagnetic interactions and so on. They give these terms, and what they make, the symmetry that we have there, what this makes sure is that the charges, so the electromagnetic charge and the charges of the other interactions, that they are conserved. So this charge conservation is yielded by such symmetry under these phase transformations. So it's really, really interesting. So I hope you could in some way follow what I was saying. So if not, it's not that important. Let's just understand there are symmetries that are purely mathematical, but they still have lead to physical conservation laws. And these purely mathematical symmetries imply conservation quantities in the natural sciences raise a question that already was asked by Eugene Wigner. Why is mathematics so effective in the sciences in describing the observable nature? What is astounding about this is not only the fact that mathematics provides an effective description of nature, but especially that the human mind is also equipped with the ability to comprehend it. In his paper and on the subject, Wigner writes that this is surprising from a Darwinian naturalistic perspective. He says, "It is certainly hard to believe that our thinking ability has been brought to the perfection it seems to possess by Darwin's process of natural selection. If like Galileo we consider mathematics to be the language of the natural sciences, then it is indeed remarkable that humans are able to speak this language. In the case of everyday physical effects, this can perhaps be explained speculatively from an evolutionary perspective by adaptations due to selection pressures. However, this does not explain how it can be that events that cannot be directly grasped by humans, such as those of quantum mechanics, can be accurately described using the same mathematical language." Wigner writes, "This shows that a mathematical language has more to commend it than being the only language we can speak. It shows that it is, in the truest sense of the word, the right language. From a viewpoint that believes in creation, this comprehensibility of mathematics is not strange, but rather to be expected. In the Gospel of John, so John 1 verse 1 and the following verses, God is presented as the Word, or in Greek, the Logos. This is the same word from which our word logic derives. Furthermore, it says that everything was created through this Logos. The creation account also describes that man was created in the same image or likeness of God. It is not surprising that man, who is created in the image of the same Logos, or the same logic that also created the world, is endowed with the ability to speak and understand the logic or the language of this logic. The effectiveness of mathematics in the natural sciences, which Wigner admired and which is illustrated here by the Noether theorem, can therefore be interpreted as an evidence of creation. Thank you for listening to the Follow the Lamb podcast. Now it's your turn. Please let me know what you think about this episode. If you are on Spotify, you can use the comment section below. Otherwise, you can go over to my Substack, youfollowthelamb.substack.com, and there you find all the podcast episodes as articles, and you can read them again if you like, and also comment on them. If you want to contact me directly, feel free to use the contact form at my webpage sci-faith.de/en/contact. Please also note that this is an independent podcast, which means it is only produced and marketed by me, and therefore I need your support. Share it with your friends, relatives, and everyone you think might be interested in hearing these episodes. Also, do not forget to give this podcast a 5-star rating and subscribe to it to never miss an episode. Thank you very much, and follow the Lamb.